Right, so you should be seeing a PowerPoint presentation. Can you see that and can you hear and see me? Although seeing me is optional, but hearing me is probably going to be quite useful for this presentation.
Yeah.
Excellent. So I can no longer see Zoom because I'm presenting in full screen. But if there are questions, please drop them in the chat or save them for the end if you can. But if there's something that's obviously important during it, then please do shout up. My talk today is going to be geospatial for the Geocurious. So this is potentially going to be a little bit different to some of the talks that you would get at these sort of language-specific meetups, in that I'm actually not really going to talk about implementation specifically here. This is more going to be a theory presentation. And I will dive into a couple of areas of what is hopefully a niche area of engineering that you may or may not have heard of, Esri folks aside. I don't work for Esri, I'm not affiliated with Esri. It's entirely coincidental that we have a geospatial company hosting it, and my area of expertise is also geospatial. I just hope that you find this interesting. And just a small note, but I've been off with a chest infection for the last week, so apologies, but I'm going to be drinking water profusely during this presentation. So a bit about myself. Who am I? Why am I talking? Why should you maybe listen to me? You don't have to listen to me. So I've been a software developer in the industry for about 20 years now. Most of my experience has been in simulation distributed systems. I started my career in C++. I then moved into C#, and in the last couple of years, I've moved into working in Rust. And I would never go back after that, but that's a separate discussion around language choices. I currently work for Helsing. Helsing is a European defense technology startup founded about 3.5 years ago. We've got offices in Munich, Paris, London. We've just crossed over the 400 people mark. I joined the company about 3 years ago. I've done a couple of things there. I've led the distributed systems team. I've worked on large scale simulations, and more recently I've been working in business operations. But it's actually part of my responsibilities at Helsing, which is interviewing, that sort of gave me the spur to do this talk, because one of the really nice things about interviewing candidates is you get to hear a massively diverse range of experiences and backgrounds, and you get to probe into bits of engineering and bits of technology that you just wouldn't ever have a cause to know about otherwise. And I always enjoy those discussions with people because it always spawns a little bit of interest in your brain. So I thought I'd bring a little bit of that today to this presentation. And before I was at Helsing, I spent most of the rest of those 20 years at a company called Kamer, which was a small startup in Cardiff. We were making software for the telecoms industry, roughly in the area of designing and optimizing cell phone networks, so telling you where to put cell phone towers, how to orient them, how to configure them, and how to get the best out of the investment you are making in deploying your 4G network, your 5G network, whatever it is that you're rolling out. So my presentation today is around geospatial data. So geospatial data is, put simply, anything that you can represent with some sense of geographical coordinates. So examples of things like this are GPS traces. You may have more abstract things like maps of census data where people live. You think of traffic flows, and you think of business locations. These are all things that are geospatial data. There is infinitely many different things that can also be geospatial, but it's basically anything that you can tag a piece of data with a physical real world location. And specifically, I'm going to talk a little bit about how you build really big systems of those. I'm going to dive into a couple of different bits of technology that let you do that. So you may sort of now have heard the word geospatial for the first time, and you may think, that's quite interesting, but it doesn't really apply to me. Well, geospatial is actually something that most people use in their day-to-day lives without potentially even realizing they're using a geospatial or geodata rich application. There's a couple of examples of this here. So you've got things like Uber. If you think about the Uber app, if you've ever used it, when you set your pickup location, not only are you putting a point on a map, but you also get this really cool little view where you see all the little taxis that are near you driving around the map in real time. And that's a case where they've used this sort of rich bit of geospatial data to enhance the user experience of their application. And another example in the middle here is this Cardiff's bus app, very commonly built type of application. You can go into the app, you can see all the bus routes, you can click on the bus stop, see when the next bus stop turns up, see all the buses along the route, see how long it's going to be until the next one. And then you get things like Deliveroo's app, where you get that great little icon of the rider bringing you your delicious takeaway. Then you obviously get things that are primarily geospatial applications, geodata applications. This is Google Maps here, showing its spectacular 3D view, but this is an application that exists primarily to give you some geospatial data as its primary function. Then you've got some really interesting nerdy ones. This is my favorite. This is Flight Radar. If you've ever been onto Flight Radar's website, it's an amazing site where you can go and you can see most of the planes that are flying around the world in real time. If you sit on the page, the icons will keep moving because they're moving in the real world. You can click on a plane, you can see where it's come from, where it's going to, what altitude it's at. You can see the line of where it's been. You can see all the information about where it's been previously. Flight Radar is actually a really interesting one because it's also all user source data. So they've built this huge application where they're actually reading in from these little boxes that they ship to people that picks up the transponder transmissions from planes, and they ingest all that into their application and feed it in real time out to you as you're viewing the map. And then finally, you get some other ones. This is a very similar one to Flight Radar, but this is trains. This is Signal Box. It shows you all of the trains here, the South Wales Valleys, very similar thing. You can click on the train, see where it is, see where it's going next, see what time it's going to be at particular stations. So that's sort of a little bit about where you may have come across geospatial data in your day-to-day lives. But what actually makes up geospatial data? Well, if you've ever sort of done any work in any way whatsoever with computer graphics or even simple drawing in a computer graphics API, there's sort of two main types of data that you deal with. There's vector data and there's raster data. And the difference between the two is that vector data it's just some information that's made up by a bunch of XY coordinates, just discrete points that say at this specific coordinate there is some information. So you may take this example here where we've got these blue points. They may just be individual points. So you may be drawing a dot onto an image at coordinate XY, or you may have something like a line shown here in red that's actually a set of XY coordinates. But the entire descriptor of what that line is just those sets of coordinates. Then you have things like raster graphics. Raster graphics are essentially bitmaps. They're just an X by Y grid where every cell in that grid or every pixel is the same size and it has some value in it. Typically, you would have an RGB value in there because you're drawing a computer graphics to the terminal, or in the case of geospatial, maybe you're drawing something like a satellite image. So you've got a raster graphic that's a big bitmap of a satellite or an aerial image. But you do also get a bunch of other types of information in here. So you also get things like terrain maps, maybe temperature models, wind speeds, depending on what type of application you're doing. Primarily today, I'm going to focus on vector graphics. And that's really going to be the thing that I'm going to talk about in my sort of algorithm deep dive. Just to show that in a little bit more detail. So this is some vector graphics. This is from OpenStreetMap. OpenStreetMap, if you haven't seen it, it's imagine Wikipedia for maps. You can basically have it's a website you can go onto and it has a map, but also you can edit and draw into the map. And this just shows different types of vector data. You've got sort of point data up here that displays all the trees. It's just an XY coordinate that says at this point there is a tree. You've got the paths, which are made up of lines. And then you've got polygons like the outside outline of Cardiff Castle here that's made up of a series of points. And then the raster equivalent of that, showing the same area, where it would be something like this. It would just be a satellite image of that area where you've got an X, Y grid, and in each cell of the grid, in each pixel, you've got some value, an RGB value here, and then you end up with a satellite image. So as I said, I'm going to talk a little bit about vector data and how we deal with vector data in some of these large systems where you need to deal with a lot of data. And I'm going to talk a bit about how you would deal with those in sort of the primitive first, and then talk about how these things can be used in sort of larger scale distributed systems where you're building really big data stores. So one thing that you may want to do with vector data is a typical thing would be say, okay, I've got a whole load of data that represents data all across an area or all across the world. And I want to find some data in a specific area because I want to draw a map or I want to perform some sort of analysis with that data. How do I extract from that data store all of the data that covers a particular area? So the way that we start with this, so I'm going to use the example of polygon data here. So these sort of regions which are defined by sequences of coordinates. Well, the first thing we do is we define something called a minimum bounding rectangle. So we attempt to simplify that geometry and we say, okay, well, there's a complex shape here, but inherently I can sort of simplify this shape to being, in the case of this blue polygon here, well, I can describe it as just being, it's some data inside of this blue rectangle. And the same with the red here and the same with the green. And the really nice thing about doing that is you've defined, okay, this is the maximum extent that this polygon covers. And I can also represent that data with just two coordinates. I can just store the two corners, the two opposing corners of this rectangle. And then I've created a way of saying, okay, there's a bunch of data, but in its simplest form, it's all within this particular rectangle that's described by these 2 points. And if I do that for every single polygon within my data set, I draw a little rectangle around it, the smallest rectangle that I can. What you can then do with that is you can jump to the algorithm's best friend, a tree, and we can start building a tree out of that data. And if we build a tree out of that data, we can query that data. There are a bunch of different algorithms for doing this. This is just a description of one, something called an R star tree. And basically, the way that this works is you take each of those rectangles that you've just drawn around something. So these red rectangles here, you take pairs of those and draw a rectangle around them. And then you've described the area that minimally encompasses those 2 polygons. And then you do it again and again and again, and you've effectively built your tree. So if we think about this red rectangle R7 here, it sits in a pair with R6, which is described by this blue box. And that blue rectangle sits inside next to this other blue rectangle R4. And that all sits inside of a rectangle called R1. So we've defined a way of saying, hey, I can take this data that I have and I can build some sort of tree out of this data. And once we have a tree, we can query it. So it's simply a case of, okay, if I want to find some polygons that are in a particular area, I can start at the root of the tree. I can look at the nodes within that leaf of the tree and say, do any of these overlap the area I'm looking for? If they do, you recurse into those and you recurse down. So your sort of standard simple tree traversal is the way that you would then be able to query that data, and you very effectively be able to say, okay, how can I find the data that I want? Well, we've built a tree and I can just traverse the tree to find this data in a very large data set that I'm after. So that works, and that works really well. But there's a couple of problems with this if we want to build ourselves a really big system. And those problems are, well, the leaves that we've just built inside of that tree, they're arbitrary. They're a product of the data that we've put into the tree. And what I mean by that was if we were to change the data that we've put in even slightly, we could end up with a tree that's laid out entirely differently to the one that we just saw. And every time we insert something into the tree, we've then got to make a decision about how we rebalance the tree. And if we need to rebalance the tree, it then means that we've got to potentially change the look of that tree again during runtime. And this isn't going to work for us for a bunch of reasons that I'll now explain. So if we wanted to build a distributed system, what that means is we need to find some way in which we can share the work and share the storage of what we're doing across a whole bunch of different machines. And the way that we can do that in the simplest is we can redefine sort of some common reference system with which we're going to describe all of our data. And if we can define that reference system, we can define a structure that's agreed ahead of time for all of the data that's going to be inside of our system. And this is where the previous approach falls down, because if we've got arbitrary leaves within a tree, we no longer have agreement across the system of how that data is structured and how it's represented. And this is the wrong that we need to undo to build a distributed system. Because if we can do that, and if we can agree on how we're going to structure and store our data, and ultimately, if we can reduce our data to basically describing our data by some pre-computable or recomputable ID, we can leverage all of the existing tools that are used for building distributed systems to store our data for us. We can actually achieve geospatial data storage without having to build anything new, but we do have to think about how we structure our data. So for the rest of the presentation, I'm just going to talk about two specific algorithms that allow us to structure our data in a way that we can distribute it across a really large system, and what you can use those for. And to explain the first one, I'm going to explain a piece of mathematics, and this mathematics is something called a space-filling curve. And you would look at this and you would immediately go, that's not a curve. And you would be entirely correct, because that is not a curve, and it shouldn't be called a space-filling curve, because it's clearly a bunch of 90-degree corners. But a space-filling curve is a really neat concept, and the concept of a space-filling curve is, given an area, I can define a line that passes through that area, visiting every part of that exactly once, and it never crosses over itself. So on the right here, I've shown an example of one way of defining this, which is called a Hilbert curve. Again, not a curve. I didn't name it. And I've shown that Hilbert curve for a bunch of different sort of depths or accuracies. And effectively, what we've done here is we've taken a longer line each time and fit that longer line inside of the square area, whilst keeping those same guarantees. This line passes through this area, and it passes every section of this area, and it never crosses itself. There are a couple of other really nice properties of the Hilbert curves, or space-filling curves in general, which is, if you were to take this line and you were to lay it flat, you could take any point on that line and deterministically say where that point would fall within this square. It's XY within the square. And that means you've set yourself up for defining a way of easily converting between an XY coordinate inside the square, so maybe this point within the square, and where it falls along that line. And this is super important for the next thing. So one of the ways in which we can structure our data is this really cool library called S2. And this was first developed by Google. And they said, okay, what if we take this space-filling curve concept, and what if we lay that curve across the entire Earth's surface? We've now been able to define a line that passes all the way across the Earth's surface once, and exactly once. And because of the guarantees we just talked about, because we can take that line, stretch it flat, and give every section of that line a unique coordinate, we've given a way in which we can describe a section of the Earth's surface with a unique ID that we can map both between that flat line and the surface of the Earth. And basically what that means is at any point on the Earth, you can generate a unique ID which tells you where along this line it falls. And this is going to be really useful for us for storing a bunch of different information. But the types of data you can store with this would be things like GPS coordinates. I'm going to show an example of how that works. So there are a couple of other nice little properties about about S2 specifically. And that is the parent cells are well defined. And what that means is when we looked at that previous graphic and we had those lines that got longer and got sort of more compact each time, so we had a line that was even longer and let us refer to a specifically smaller area. Well, it's really easy for us to say, okay, well, what is that point in the coarser version of this, and the coarser version of that, and the coarser version above that? And that's really important because it lets us say, okay, well, actually, let's take each version of that line at a different size, and we then have basically a way of defining a tree, which is going to be really handy for us. There's a couple of downsides to S2 itself. Because you have 90-degree corners, it's really bad for defining adjacency, saying, okay, the line next to me, to the right of me maybe, because of the way that it traverses the area, that position may be way further along the line. And you have two different ways of thinking about the things you're next to. You can share an edge with them, or you can share a corner with them. And that's not quite so helpful in another example I'm going to show later. And that it basically means that because we've been able to make a tree out of this, we've given every possible item inside of that tree, we've predefined, if it was to exist, what ID would it have within that tree? Where would it fall within the tree? And this is really handy because going back to that guarantees that we wanted to talk about for distributed systems, we wanted to say if we were to put this data item in the tree, we need everything in the system to agree where we would put this data item in the tree. And that means that we can independently, two different systems can say, I would put this item in the tree here, and they would give the same result. And this graphic on the right here actually shows a really interesting thing about S2. It's not just one curve, they've actually stitched 6 curves together and wrapped those around the Earth's surface with maths which I will never in my entire life understand, but I've been guaranteed do work. So let's then, okay, we've got this concept. So let's think about how we would then use that concept. And one of the common places that you will see S2 being used, and you will actually use S2 without realizing it, is in Google Maps. And when you're in Google Maps, as you zoom in and zoom out, you see all those little icons of all the businesses coming in and out of the map. And the way that they do this is if you were looking at the map within the blue area here, they run a little algorithm that says, okay, given all those curves that I've predefined, what cells within that would pass through the area of the screen that I'm looking at? And it would say, okay, you would have these 10 cells here. And this now says, okay, I need to go and ask this tree of all my data, what data exists inside these cells, and I can then display them to the user. So as you're zooming in and zooming out of the map, it's looking at this and going, now I need to display this cell here. And it goes off and fetches what are the business icons or what are the road names? What is the traffic flow for this particular area? So then let's think about how the inverse of that works, because it might actually explain a little bit about really sort of explain a little bit more clearly how this data is structured. So a common use case that you want to do with this is then, I want to put a marker on the map. And let's, for example, let's say that it's this Cardiff Market icon here. When you're zoomed all the way out on the map, you don't want to see a little icon for Cardiff Market, especially not if you're zoomed out showing the whole of Wales. But as you start to zoom in on Cardiff, you'll see things come into the map and you'll see this Cardiff Market icon will start appearing. But there'll also be a point where you've zoomed in far enough and it'll go, you don't need to see there's an icon saying Cardiff Market exists. We need to show all of the icons of the individual shops inside Cardiff Market instead. So a common thing that you'd want to do is you would want to say, okay, I've got something I want to put on the map at this XY coordinate, and I want it to display when the user is zoomed in this range here. So when they're not too far in and when they're not too far out in this zone here, say between two concrete numbers, 10 and 15 in this case, I want this piece of data to exist in the store of all the data for this area. So the algorithm for that is quite straightforward. You simply take the deepest zoom level you have, so 15, the most accurate thing, and you say, what's the cell ID for that? And it's going to give you back some sort of hash looking number. And this is where S2, they've actually done a little bit of complete magic with this. To work out what the parent of that is, so what the thing at zoom 14, zoom 13, zoom 12, or as you would think about it in a tree structure, what the parent node of that tree item is. It is simply that same ID, but you truncate the last character. And that is the ID of the thing that you get in the tree, which makes traversing this tree incredibly easy. And it also means that you now know, okay, I want to put this thing in at zoom level 15 or zoom level 14. I need to take this section of the tree and insert my data to it. And it's as simple as that. You just take these unique keys, and in whatever thing you're using to store your data, whatever distributed store, whatever database, you simply just lock these individual things and you update them. And it means you've performed an operation on the tree where we've no longer had to balance the tree. We've no longer had to think about how other people are using the tree. The people using the tree in southern Brazil are not interested or affected in any way by the work that we've just done in Cardiff to insert this new icon for Cardiff Market. So that's a little bit of an overview of S2. I think I've got around about 10 minutes left, so if that's not true, do shout out on that. But that's a data structure which is really good for storing sort of discrete pieces of information that you want to go and look at, or you may use to build something like a map. But there are some super interesting other ones. I'm going to use the rest of my time to talk about Another similar in concept, but different in the way that it works for a very interesting reason. And that's going to be H3. Um, and H3 was, it is a piece of software that was first developed by Uber. And they had a similar idea to Google. They said, we need a way of representing every point on the Earth's surface with some unique ID so we can store data all around the Earth's surface in at massive scale and work on that data independently of other bits. But they decided they didn't want to use a space filling curve. And what they decided was they actually wanted to use hexagons. And they went with hexagons for a very specific reason. But in principle, their map looks the same. You have a web of hexagons instead of a line that covers the Earth's surface. It's valid at a bunch of different coarsenesses, a bunch of different zoom levels. So you can see here you've got big hexagons, small ones, even smaller ones within those. So they decided that for what they were going to define, we could have up to 15 of those where you have whatever very large number that is. So they've defined that many different places on the Earth's surface as the most accurate amount of quantization they can give to any piece of data in their system. So what does H3 do? Well, it does the same thing as S2 in that it says every one of these hexagons has a unique pre-computable and recomputable ID. So a reliable identifier for each one of these hexagons all the way across the Earth's surface. Every hexagon that could fit on the Earth's surface has a unique ID that can be computed. But they chose hexagons for a very specific reason, and that hexagons have perfect adjacency. And what that means is there's only one thing that you're adjacent to, and that's something you share an edge with. And you always share an edge with it. You don't share corners with things with hexagons. So if you look at these hexagons here, the hexagons that are next to you share a full edge with you. And that's going to be really important for what Uber wanted to use it for, which is they wanted to use it for area-based analysis. They were really interested in defining a data structure where I can not just put a piece of information in a specific point, but also make the points around this piece of information be impacted. And you can't do that unless you can easily define what is the thing next to me, what is the area next to me. And that might make a bit more sense if I talk about this and what it's used for. One of the primary examples of what Uber used this for is surge pricing. Like it or hate it, I think it's a terrible idea, but surge pricing is this mechanism when there's a lot of bookings in a particular area, they put the price up because they'll say, there's a lot more contention for taxis, it's a lot busier, therefore we're going to charge a surcharge for the system. And the way they do that is they take this hexagon mesh, and every time they make a booking, they put a number into one of those hexagon cells. And they also put a slightly smaller number into the cells around it. And what happens here is once you start getting a weight of bookings for the area, that area starts growing and you start getting a larger area that grows. And if you think about what that looks like in computer terms, I said I wasn't going to show any code, but I've actually shown what is some complete garbage pseudo Rust here. So what they actually do is every time you make a booking, they take your lat long, they convert it into what is the unique identifier of the hexagon that falls into. They go to whatever distributed store they're using. Because you've got a unique ID, it can simply be something as straightforward as an in-memory Redis cache and say, hey, in this cell, increase the number of bookings by 1. This is 1 more booking than there was just now. But they can also, because it's very easily definable, say, that's true, but also go to all of the neighbors of this cell and increase their booking by a small amount because there's a slight bit of bleed from this cell into the adjacent cells where you're saying, okay, there's an impact I have on the areas around me. And over time, this will build up into an area. And when you're booking, they simply do the inverse of that. They work out where your cell is, they go to the distributed store, and it tells them whatever score has been put in there. And they say, is this above the surge threshold? Yes, it is. Then I will apply the surcharge to the booking. And that's why they went with this slightly different approach. H3 itself is not impervious. It has some issues, and I'm actually missing a slide here for some reason, but I'm going to jump back to this one to explain that. And the issue that H3 has is when you take a hexagon, if you want to divide it into smaller hexagons, it's only approximate. So if you look at these ones sort of in the corner here, where you have smaller hexagons inside your hexagon, they don't fully cover, and there's a bit of overlap, so it's only approximately covered. And the problem that this has for them is that they say, if you want to do this analysis, you have to agree on the size of hexagon you're going to use across your system before. And if you want to change it whilst the application is running, you need to reprocess all of your data because it's not guaranteed, like in S2, that the hexagons that you have, when you divide them, the data would still be inside that same hexagon. It may fall into one of the adjacent ones because you just simply can't divide a hexagon into smaller hexagons. It doesn't fit. You can only do an approximate case here. So you have these little areas of overlap that you see between the different zoom levels. And this effectively means that H3 is great, but it's not a true tree in the same way that H2 was. It's an approximate tree. And that's okay if you only care about approximate things, but if you care about very specific, accurate information, it's not the right tool. So that's just a little bit about S3, S2 and H3. And that's everything that I had to talk about today. If you want to read a little bit more about them, there's a website for S2 and H3. There's also a couple of websites where you'll find a little bit more information about just sort of geospatial data in general. And I appreciate I've just hit the end of my time slot, but I don't know if there are any questions. I think there was some stuff in. No, I'm not going to talk about Z order curves. Absolutely not. And yes, in computer graphics, it's a bounded volume hierarchy. Yes.